Okay, welcome everyone to Software Architecture and Design 2. My name is Rick Kaisman. I'm from the University of Hawaii, and I will be chairing this session. Hopefully you all know what is expected of you and what is the protocol for all these sessions. 5-minute talks times six papers, and then we'll have approximately half an hour for discussion following that, where anyone can ask a question of any of the authors of the other papers or of the papers. So given that we're on a tight time budget, I would like to jump right into it. The first paper is Building Maintainable Software Using Abstraction Layering. And John Spray, I assume you were the presenter?
Yes. So can I go ahead and get started?
We cannot hear you if you think that you're speaking.
You cannot hear me?
I can hear him. I can hear you, John.
I can hear you, John.
I can also
Okay.
hear you.
Okay, so
You can hear John?
And
yeah,
but I can also hear you.
someone relay that to Rick that you can all hear me and he can't.
You can hear John. Oh. Okay. I have no idea what's going on.
Do you want me to leave the meeting and rejoin Rick? Except you can't hear me ask that.
All right. Well, if you can hear, then John, you continue speaking, and I will try and look into my audio problems.
Okay. Can someone ask Rick if he can hear all of you?
Yes, John, I can hear you.
Gaston, can you ask Rick if he can hear all of you?
Oh, yeah, I hear you. You can hear me, John?
Yeah, but can Rick hear you, Gaston?
Okay, so no, I
Because
don't
I'm
have...
just wondering if I should leave the meeting and then rejoin.
I don't see the option to record the presentations in my session.
All right. Well, I'll just get started.
I can hear everyone, so just begin.
Looks like Rick has rejoined. He's left and rejoined. So I will, I guess, get started. I shall share my screen.
Can you hear me?
Infinite sharing. So that's what we want. Hopefully you guys can see my slides. All right, so hello everyone. My name is John Spray. Our paper is about a new reference architecture called Abstraction Layered Architecture, or just ALA. So what is Abstraction Layered Architecture? ALA is an architectural pattern. It organizes code at all larger scales of an application or system. It's applicable to any software, monolithic or distributed, for which you want the quality attribute of maintainability or the related attributes of understandability or constant complexity regardless of system size. Fundamentally, ALA consists of three constraints. 1. The only unit of code is an abstraction. 2. Only one type of relationship is allowed, a dependency on an abstraction that is significantly more abstract than the one using it. And 3, all abstractions must be small. The three constraints give rise to important emergent properties. The abstractions form discrete layers, which we name by the type of abstractions that tend to live in each layer, such as domain abstractions. The architecture is a polyglot programming paradigm, which means it uses many different programming paradigms at the same time, such as data flow, event-driven, or UI construction, and others that you can invent. The internals of all abstractions are zero-coupled from one another. In conventional modular or distributed code that used a decomposition methodology, there is typically design coupling, or what I call collaboration coupling, between the modules or classes. ALA converts collaboration coupling into cohesion. A user story is completely represented by cohesive code contained inside its own abstraction in a higher layer. Another property is composability, expressing user stories by simply composing domain abstractions. We trained some intern students on ALA and got them to rewrite a conventional legacy application. We wanted to apply popular metrics to the two versions to compare the maintainability. These are resulting dependency graphs for the two versions. The legacy one is on the left, looking like a big ball of mud. ALA distinguishes between good and bad dependencies. All of the dependencies in the right graph are good dependencies. We actually want more of them because that means we are reusing our abstractions. Most of the dependencies in the left graph are bad dependencies and illegal in ALA. Unfortunately, commonly used metrics for dependencies, such as CBO, coupling between objects, are unable to distinguish between good and bad dependencies. If they did, they would be useful. In the comparison between the legacy and the ALA versions, the modularity, analyzability, testability, and reusability were all higher for the ALA version. The modifiability of the ALA version was lower in the beginning, while new domain abstractions are frequently needed for building new user stories. But the modifiability improves over time as the domain abstractions mature. The total effort to build the two versions was approximately 12 man-years for the legacy version and 3 man-years for the ALA version. The usual experience of developers is for modifiability to decrease over time, but for ALA it increases over time. It is said that 90% of commercial software is under maintenance. The metrics indicate that significant cost savings are possible. Thanks for listening.
Thank you. So again, we'll save questions till after the talks. So without further ado, we will turn to just enough, just in time, just for me.
Am I sharing probably? Hello? Hear me? No?
Yep, we can see you share.
Okay. Do you hear me?
Yes.
Yes.
Okay, cool. Well, thanks, Chair. Thank you, everyone. Buenos dias, buenas tardes y noches. My name is Zheng Li. I'm from the University of Concepcion in Chile. Today, I'm going to talk about some fundamental principles for engineering IoT native software systems. I have to skip the explanation about IoT, but let's clarify that when we talk about IoT system, we are actually focusing on the software systems, okay? At least in this context. For the IoT native software systems, it has been widely recognized that we need not only new tools and technologies, but also a new understanding of the systematic development process and tasks. And we have been, suggested zooming out from the technology layer to a much higher level view of the whole system and its engineering, okay? So in terms of the higher level view, we emphasize the software engineering principles because they are the abstractions of best practices. Then how do we identify the best practices? Well, firstly, we observe. So we have got the first principle just enough, mainly based on our observations. Actually, we believe this has been a common sense now. You know, it's widely accepted that we should avoid over collection, over processing, over storage of data. It's not only about the performance and resource concerns, but also about the privacy concerns. Actually, today's keynote speech in my time this morning just mentions how important the privacy preservation is for and in software engineering, right? It's a happy coincidence. Although it's possible that we might have some trade-off. For example, we may intentionally cache some intermediate results to reduce the data processing workloads. Okay, and the second principle is just in time. This is mainly based on our kind of work on improving the communication efficiency in the IoT environment. Although we may also have some space-time trade-off. It's impossible to explain these techniques now, but we can imagine that we have quite a few different techniques to improve the communication efficiency in the IoT environment. However, we should also know that these techniques all introduce extra data processing workloads. No free lunch, right? Especially for those sophisticated techniques. So there's always a frequent question like, is this really worth it, especially for those sophisticated techniques? Well, we have been following our second principle just in time to answer this question and also to guide our research. Okay, we argue that as long as we guarantee the key data to arrive at least in time, and all the key tasks to finish at least in time, well, it'll be worth it. Okay, so this is the second principle just in time, and the third principle just for me at this current stage is mainly a proposal. Okay, in our opinion, and this principle we argue to follow this principle to make those functional units and sometimes individual devices smart, but in a very selfish way. And this principle is try to address the problems of largely relying on the orchestration mechanism. You know, most of the current IoT solutions largely rely on these controllers. If we try to avoid using the central controller, we have to introduce new local controllers. So controllers everywhere. Then in the IoT environment, this could be a big challenge. So following our third principle just for me, well, we can narrow down our focus, but we can increase our awareness of the environment. I mean, for those devices or the functional units. For example, in this illumination scenario, let's imagine I am the ceiling lights, okay? So what I need is probably a semantic notification, all right? Then I will make my own decision. Should I turn on and off or off, okay? I don't care about who sent me this notification, no matter from the door, from the projector, or from the movement of voice, all right? Because these are not my business. In contrast, I should be aware of those branding sensors because their information would be useful for my business logic to make smart decisions, okay? So this is the third principle. To conclude, actually, we confirm the existing conclusions by many other researchers. We need dedicated efforts, techniques, and theories for engineering IoT native software systems. And we believe we need more principles because some principles can be more fundamental and some others might still be technical. All right. Muchas gracias. That's all.
Thank you. Thank you. Okay, so we will now move to our third presentation towards a reference software architecture for human AI teaming and smart manufacturing.
Okay. So can you see my screen?
Yes, we can.
It's an infinite,
Perfect. So, good morning from Austria. My name is Philipp Heindl from the Software Competence Center in Hagenberg in Austria, and my talk is about reference software architecture for human AI teaming in smart manufacturing.
Oh, sorry, Philip. I'm seeing your screen like in an infinite regress? Are other people just seeing the screen? For some reason, I'm cursed today with technology. Are other people seeing the screen properly?
I'm seeing the same as you, Rick.
We don't see slides. It's shame.
We don't see slides.
So maybe you shared the screen instead of your slides.
Let me try it again. Better?
Yes.
Perfect. Okay. So let me briefly summarize the key challenges that we would like to address with this reference architecture. So the first thing is the scalability for an IoT data processing. And for this regard, for this concern, we opted for a Lambda architecture that I will briefly describe in the next slides. And the second key challenges that we would like to address with this software architecture, particularly for teaming, for the collaboration between humans and AI in smart manufacturing, is the validation of ethical policies. So thereby we can roughly differentiate between two challenges, between the formalization and the operationalization. So this means that we need to find a way to introspect, so for the autonomous runtime verification of the AI system. And the second main challenge is under the validation of the ethical policies is the validation, evaluation of the policies. So basically this means that we need to find a way to check for the compliance with context-specific ethical policies, for instance, as already outlined by Google. This is the second reference here. The third main challenge pertains to relational machine learning and on knowledge graphs, and thereby the main challenge, so to say, is the performance impact. Because when you calculate these graph embeddings, this means that you transfer the graph representation to vector representation. This usually involves a very large performance overhead. And you can think if you are in an industrial machine setting, in a production environment where performance of course also matters, this is a very critical concern if you need to transfer these graph to vector representations. And the fourth main challenge that we aim to address with this reference architecture is the experimentation of data and algorithms, particularly for smart manufacturing. And thereby we see the definition, the operation definition of the evaluation criteria of the experiments as the main challenges, particularly if you would like to have non-experts to use such a, let's say, domain-specific language to explicate these evaluation criteria. And lastly, also we would like to find a way to optimize the integration of qualitative expert feedback. So this is kind of this human in the loop a manner where we would like to integrate this feedback from the experts. But normally this is a manual task, and our idea is to integrate that in an optimized manner. So of course, I can't talk within the 5 minutes about every detail of this architecture. This should just give you a short impression of what we are talking about and what this reference architecture consists of. So we have 3 colors here, which indicate the 3 parts of the Lambda architecture. I would like to start with the batch. So basically the batch layer in our reference architecture covers all the components that are used to author and import the models that are required by such a system. So this basically means the definition of the teaming aspects. So this means the models that somehow define how the computer or the AI interacts with the human and how to interpret this interaction. Second, the speed layer basically, the one hand covers the production line systems, where of course all the data from the IoT systems and the contextual systems, manufacturing systems, and so on need to be acquired, transferred, and integrated into the system. And the other parts of the speed layer consists basically of the knowledge graph, where we differentiate between a static and a dynamic subgraph. So also to somehow cope with the performance requirements that we anticipate. The other thing is the teaming engine, and the teaming engine basically is the heart of the whole architecture, so to say. Basically, it takes the models and orchestrates these interactions between the human and the AI. And the third component of this speed layer is the graph-based machine learning engine. And hereby I would only like to emphasize the calculation of the graph embeddings, because this is mainly this subcomponent that we need to focus most when it comes to performance. And the other parts mainly deal for the serving of the data. So this means the operation support. So this is the direct interaction with the operator, and the machine learning experimentation. So this is, as I said, this covers the domain-specific language and so on, and the interpretation of the feedback of the experiment, and lastly, the introspection and the monitoring of the whole system.
Philip,
Last slide.
your slides are not forwarding, and you're more or less out of time. Unfortunately.
Okay, this is the last slide, so I could also skip this because this is just a discussion.
Okay. Okay, thank you.
Should I stop?
Yes, I think that's
Okay.
Thank you. Okay, more technical difficulties. Well, we'll get through this. Thank you. Our fourth talk, Software Engineering for Responsible AI. And Qinghua Lu, I saw you join the room.
Let me share my screen. Can you see my slides?
Yes.
Yes, we can.
Yeah, thanks everyone. Thank you, Rick. So I will be presenting our empirical study on software engineering for responsible AI. First, motivation. So there are many serious concerns about AI systems' ability, whether they can behave or make decisions in a responsible way. And there are many AI ethics principles released by organizations and the government. But the problem with these principles is they are very high level, and they do not provide concrete guidance on how to build responsible AI systems. For example, one principle is human-centered values, but the principle itself doesn't explain how the human value can be designed for or implemented in the development. So in this paper, we identify two research questions. The first one is, what are the current state and potential challenges developers are facing in dealing with responsible AI issues? The second one is, how can these principles be operationalized into concrete practice that developers can use through the life cycle of AI systems? So in our work, we interviewed 21 participants from a research institute. We asked them what principles they considered in their AI project and how they implemented this principle in their project. So that's the answer. That's where we get answer for research question 1. And for research question 2, we identify a set of process patterns and design patterns based on the interview and the review results. So the table on this slide shows the incidence of themes related to AI ethics principles. So in our project, we use Australian version. So you can see the top 3 principles are the most discussed principles in the interviews, and human-centered values is the least discussed one in the interviews. So in our paper, we summarize the major findings. This group is for the overall development process. The first finding is on ethical risk assessment. So the current approach is just one of type of risk assessment approach. But for continual learning, so some participants, they mentioned it requires dynamic and also extensible risk assessment for different contexts, like different culture or different application domains. The second finding is on trustworthiness and trust. So they are different, two different concepts, but often mixed in use in practice. So some participants mentioned we need process and product mechanisms to deal with the trustworthiness of AI systems, but we need to offer evidence to users to improve their trust. And one way to improve trust is attaching ethical credential to AI components, because currently the vendors, when they create a new AI component, they usually just assemble different components. So we can, like, by attaching ethical credential to the third-party component to improve trust. And the last finding is AI model need to be integrated with the system to perform the functions, and this integration usually creates new behavior and dynamics. So we need to have the end-to-end system level solution rather than algorithm level solution, because the ethical issues, they can happen at any step of the life cycle. They can happen at any component of the system design. The next group is on requirement engineering and design. So the first one is ethical requirements, usually just stated as high-level objectives in the project proposal, but it's not specified in a verifiable or measurable way as expected system output or outcomes. And one major architectural design decision in AI system is whether to adopt AI or not. So we could consider to have AI component like designed in a flexible way. Like we can activate the AI component or switch off the AI component at runtime, or change the change from the automatic decision mode to the suggestion mode. And for some principles, so there are trade-offs between different principles, like between privacy and accountability, or between privacy and reliability. So the current practice is usually just follow one principle, but override the other one. So we can consider to have design patterns to deal with the trade-offs of different principles. And explainability and interpretability are two new quality attributes in AI system. So some participants, they mention when we provide explanations, we need to consider the user's background and also preference to improve trust, like using their familiar terms to explain the prediction or decisions made by AI systems. So the last group is about operation. So there's a strong desire for continuous monitoring and validating responsible AI requirements. And some participants mentioned we should not only focus on the output of AI system, like the accuracy of the algorithm. We should also care about the outcome of the AI system, like whether this AI system can achieve intended benefit, or whether their behavior is proper in a given situation. And last finding is on coercioning of data model code and configuration to ensure data provenance and traceability. And to specify the design patterns and process patterns, we create a new pattern template. So we want, like, if you look at the template, we have type approach. So that means whether this pattern is process pattern or it's a design pattern. And type of objective means this pattern is designed for improving trust or trustworthiness, and who are the target users, who are the impacted stakeholders, what stage is this pattern relevant, and which principle is this pattern relevant, and what kind of mechanisms can be covered by this pattern, whether this pattern is easy to apply or not, and benefit and drawbacks of this pattern, and non-uses of the pattern, like the traditional pattern template. Yeah, that's
You're
all.
now over time. Okay, perfect. Thank you.
Thank you.
Okay, so moving right along, our fifth presentation, decision models for selecting patterns and strategies in microservice systems. And I see a couple of the authors. Mohammed, are you presenting?
No, I Gaston.
Gaston? Who's presenting?
Yeah. Can you guys see me in my camera?
Gaston?
Yep.
Okay, perfect.
Hello, can you guys see my slides?
Yes.
Yes.
Okay, so I'm Gaston, and I'm here to present our research called decision model for selecting patterns and strategy in microservices system and their evaluation by practitioners. So microservices is an architectural and organizational approach to software development where software is composed for small independent services that communicate through well-defined APIs. Microservices system entail a significant degree of complexity at the design phase and runtime configuration from architecture perspective. So microservices style brings unique challenge for software organizations, and many quality attributes may be influenced. So both academia and industry have presented real-service solutions for microservices system in the form of pattern and strategy. So according to recent studies, most of the designs, developing, monitoring, and testing challenges are raised when application is decomposed into microservices. So to this end, we propose decision models that cover microservices design areas, such as application decomposition into microservices, microservice security, and microservice communication, and service discovery. So the aim of our study is to represent the decision models that assist practitioners in selecting appropriate patterns and strategies for decision-making microservices system. Having said this, we define 4 types of decision models, which are applications decomposition, microservices communication, microservice security, and service discovery. So in order to conduct our research, we defined 3 steps, which are identifying microservices patterns and strategies, modeling decisions models, and evaluating decisions models. So in our model, we use business process modeling notation to describe our decision models. For example, in this slide, the audience can see that we use gauge to describe alternative, and we also use plus signs to describe the positive impact and the minus sign to describe the negative impact of quality attributes. So as a result, I'm showing here our first model, which is application decomposition. And you can see here that we have several options that are composed by microservices patterns. And of course, we have other options that considers another patterns. In this case, for example, scenario-based analysis, graph-based approach, and data flow-driven. Regarding microservice security, we have 3 kinds of decision. The first one is application level security, which is corresponding microservices patterns. Then we have communication level security and the current components pattern. And finally, code level security. Following the same idea, I'm presenting in this slide the microservice communication decision model, which is composed by 2 decisions which are in client interaction with microservices and interaction between microservices. It's important to detail that these decisions are composed by microservices patterns, and you can see here in the red box the corresponding pattern for each decision. And finally, I'm presenting the service discovery decision model, which is composed by 2 alternatives, which are need to discover the services and need to register the services instance. So to validate our models, we conduct a survey around the world, which practitioners from different countries respond our surveys. You can see here that most of these practitioners are application developers and architects. The experience in the industry range from 3 years to 5 years, and experience working microservices range from 2 and 3 years. The main business domain that work with microservices is e-commerce. So in this slide, you can see the result about how the practitioners' assessment of how familiar they are with the decision model that we have proposed. So we address the question related to familiarity with patterns and strategies, decision models easy of use and understandability, and decision model completeness. In general, the audience can see that the practitioners are familiar with the pattern and strategy we have proposed in the decision model. So finally, we asked the interview to provide their suggestions for improving these decision models, and we can see that they recommend presenting departure with code, for example, measure qualitative value of quality attributes, and use decision models in an industrial microservices project. So in this slide, I'm presenting the key findings of our research. Our further research aims to focus extending the proposed decision models to explore possible combinations of pattern and strategy, and validate the model through an industrial scale case study, and finally developing a recommendation system that support automation and human decision in selecting the most appropriate patterns and strategies. Thank you for your time.
And thank you for being on time. Great. So Our final talk before we get to our Q&A is the art and practice of data science pipelines. And Suman, I guess you're presenting?
Yeah. So can you see my screen, Rick?
Yes.
Okay, great. So hello, my name is Suman Biswas. I'm from Iowa State University. So I'm presenting my ICSE 2022 paper, The Art and Practice of Data Science Pipelines. This work is in collaboration with Mohammad Wardat and my advisor, Professor Ridesh Rajan. So recently we have availability of numerous data and also different methods to extract values out of data, basically new machine learning technologies and AI techniques, which actually leads to development of numerous data science software, which are being performing very well in the recent practical world. And we wanted to study the design and architecture of such data science software. Here are two different examples of data science program and software. So basically, in the left, you can see a Python Jupyter notebook, which is taken from Keras repository. In different cells, you can see different stages like pre-processing, modeling, training, etc. In the right, you can see a large project, which also has different modules and different folder architecture for training or serving the models. So here, in both cases, we can see different stages of the pipelines. In many recent papers, we have also found different pipelines have been proposed for different purposes, like introducing new methods or or proposing new AI techniques. And we have also studied these systematically to understand the data science pipeline architecture. So this is what data science pipeline architecture, the definition is the collection of data science stages from acquisition to cleaning or curation to modeling and so on are referred to as the data science pipelines. And in this paper, we have answered like what are the typical stages of data science pipeline, how are they connected, and do these pipelines actually differ in their theoretical representation and that in the practice. So this is these are our contributions. First, we contributed 3 different representations with standard semantics and vocabulary of stages, and then we also introduced analysis framework, how we can analyze the pipelines, and then we actually contributed collection of pipelines which can be used to draw inspiration from. And then finally, we have done some comparative analysis, like what are the types of pipelines and what are the existing issues in the current state of the data science pipeline architecture. We have divided our study in these 3. First, data science pipeline in theory. Basically, we studied 71 pipelines collected from literature, and then pipelines in the small. We have collected top-rated pipelines from Kaggle competitions. So those are like standalone Jupyter Notebook programs. And third, pipelines in the large. We have collected mature GitHub projects, and then we have actually started the representative pipeline and then organization and then characteristics of these 3 different categories. This is what the data science pipeline, the representative data science pipeline in theory looks like. We have 3 different layers, and under each layer we have different stages. In total, we have 11 of such stages and subtasks. And we have seen that most of the pipelines are designed in an ad hoc manner, and currently there is no common terminology and representation that can facilitate reuse or interoperability. Here we have found 3 different kind of pipelines in the literature. So first is machine learning process, which is focused on predictive models and supervised or unsupervised learning. And second, data engineering pipelines, which focus more on the data management or analyzing or like storing large data sets. And third, the team process pipelines, which actually are workflow of human activities. This is how we actually built pipelines in the small from the wild. We actually create API dictionary, and each API actually can say which stage the data science software is going through, like pre-processing or evaluation and so on. And so we use this API dictionary and the data science, they extracted AST from the data science programs to create our pipelines representations. And then we analyze those pipelines. From our analysis, we found that like all programs fail to maintain a good separation of concerns, and especially data pre-processing actually are tangled with other stages which are making pipeline jungles. But some resolution attempts have been taken for readability, reusability, or debugging. And finally, we have these data science pipelines in the large. Basically, we looked at the large projects and we created high-level, low-level pipelines. High-level pipelines are basically looking at the architecture, and low-level ones are looking at the APIs of different of these files. So yeah, we have found these
your time is now over. So
Yes,
if you could finish up, please.
Okay, yeah, sure, thanks. So basically, we have found these two different phases, and the first one actually solves the problems in general, but the post-development phase actually takes the model artifact and then makes predictions. So this is what summarizes our paper. We have presented the state of the art and pipeline analysis and many such anti-patterns in data science pipelines. Take a look at the paper. If you have any questions, please feel free to ask. Thank you.
Thank you. Very interesting. Actually, I think we've had 6 really interesting presentations, and unfortunately, we only have 20 minutes for discussion, but I invite any of you to lob a question at any of the presenters. I have questions for all of them, but I would like to give you the opportunity. So please raise your hand or just speak up if you would prefer.
Yes, I have a question. Yes, first I want to congratulate all the presentation because it's very interesting. My question is to John. John, I think your work is very interesting. Basically, my question is, you have experience using your pattern in industrial cases?
In industry, yes.
Perfect. And how was your experience using your pattern?
Sorry, say again. Didn't catch that.
Well, basically, my question is, how was your experience using your proposal?
Oh, the experience using the pattern. Oh, very good. So what we did, we had this enormous big ball of mud application, but we knew what the requirements were. So we spent the first iteration, this is what you do in ALA, for 2 weeks, just doing the representation of the requirements, and at the same time inventing all the domain abstractions and the programming paradigms we would need. And that went very well. We were so surprised because that was like the first time we were doing that. And then from there it was just plain sailing, because you just implement the abstractions and everything starts working.
Oh, thank you.
Thank you. Other questions? Okay, I'll ask one. So this is for Jung Lee, the second presenter. How do you determine just for me in general? I couldn't get what the general principle of that was, how you would determine what the scope of just for me would be.
Right. I think the generic situation is try to think about sort of the smart devices by default. Smart devices. Okay, we have smartphones, smartwatch, smart glasses. So in the software engineering, in the software system, for if we consider those functional units, because I try to avoid using some other possibly confusing terms like microservices or similar stuff. So we try to make those functional units smart as well, so that we can match the smartness of the software side and the hardware side. And just for me means that we can avoid or at least reduce the usage of so many smart controllers. We try to make those individual components smart enough to handle at least their own business. And then eventually, at least in particular situations, the bigger business logics will be satisfied, will be implemented by the collaboration in a sort of a choreographed way.
So trying to make them more autonomous.
Yes, exactly.
Okay, I have more questions, but we need to give
Yeah.
Thank
Sure.
you. Other questions from participants?
I wanted to ask to Queen Hua Lu, so about the responsible AI. So I was wondering, like, you have talked about the ethical credentials or ethical guarantees of software. So can you give an example, like how it can look like, and where do you think the ethical guarantees can be integrated in the pipeline? Like, would it be in the pre-processing or before the model building or after the model building, like in a thorough evaluation or something like that?
Yeah, I think in our another paper, in the other paper we wrote is about design patterns. For example, we have like a black box in the runtime, so it can like collect critical data like sensor data or intermediate state data or output like the decisions made by operators or the system itself. So that can ensure accountability. So accountability is one of the principles. The other one I can think is privacy. Like we can use federated learning, so it can be viewed as an architectural pattern. So you train the model at client side, then you aggregate the result in the central server. So in this case, you preserve the client's data privacy. And also, I think we have a bill of material as a design pattern. Like you can like track supply chain information of the third-party component to ensure accountability or transparency.
Okay, yeah, thank you.
So I have a question for Philip. It's a very simple one, which is how would you go about validating a reference architecture? Its reference architectures are meant to have
Very interesting question. Yeah, basically, as the name suggests, this is kind of a reference of software architecture. And in this EU-funded project, we have 3 industry partners right now. Because otherwise, it would be very bold to say it's a reference architecture with no clue about the validation, of course. Yeah, no. We have, as I said, we have 3 industry partners across Europe, 2 in Europe, 1 in Turkey, mainly in plastic injections and large-scale manufacturing assembly of windmills, and we will instantiate the reference architecture for each of these use cases. Yeah.
Okay, thank you. Other questions from the group?
I have a question for Gaston. So this seems like a really valuable contribution, more especially as a tool for finding potential patterns for quality attributes, more than being the sole way of deciding them. So given the number of respondents to your survey who are not familiar with all of the patterns, do you agree that this is the case? It's more useful for finding out about the patterns. And also, how did you determine all the positive and negative influences on the quality attributes? Where did they come from?
Well, that's a good question. In our research, we try to define how a specific quality attribute impact positively or negatively into another quality attribute. We execute a multi-vocal review in order to know which quality attribute impact positively or negatively. We define all that relationship interviewing experts that they give us their experience about how a specific quality attribute impact in a specific design system, positively or negative. We try to make a bridge between quality attribute and microservices pattern by listening, talking with experts and how they use this this pattern with that quality attributes. So we gather all the information and we propose this model based on the experience of the experts in microservices.
Okay.
I have a question for Simon.
Yep.
Can we infer basic architectural mechanisms from the framework that you've presented? So can you basically look at the commonalities and say these are the patterns, the mechanisms, the tactics, something like that, based on your research?
Yes. So we also looked at so from practice, we have actually mined the data science pipelines and built the framework that you talked about. So we have seen that the data science software are basically API intensive, and each API can tell us a lot of those are kind of abstraction of a lot of details. So we can tell that which stage the software is performing, or what is the underlying task it is doing. So from that, we have actually shown that we can find the commonalities. We can actually try to find common patterns into different pipelines. And also there are like patterns and sub patterns, so like sub pipelines. So inside a modeling phase, we can see different data pre-processing and evaluation loop, and we can find those loops repetitively in different pipelines. So using that one in data science programs, we can find commonalities and the sub pipelines. Yeah.
So is that a future paper?
Yeah. So we did not explore that a lot because we wanted to show like what are the different types and what are the different issues that are existing. But that could be a future work to build a framework to find like interoperable pipelines, or which can be reusable pipelines, and so on. Yeah.
Thank you. We have a question from Paul Robinson in the chat for John Spray. ALA appears to be an interesting way to build something from the ground up. Is it feasible to refactor an existing application without doing a complete rewrite?
Oh, good question. That's actually our current focus of research, because most work on software is actually being done on existing software these days. Unless we solve that problem, people aren't. Well, that's what would really make it take off. If we had a tool which could analyze existing code and give you metrics and give you refactoring suggestions, tell you where your abstractions are, and give you a full path to refactor it into ALA code. Yeah, that's the holy grail that we're after.
Thank you. Other questions? You can put them in the chat if you like, or just speak up. Otherwise, I'll keep asking.
Okay, I have a question for Qinghua Liu. So firstly, I'm glad to see someone is thinking about these things. So traditionally, every time we've needed to be responsible as humans, we've been unable to do it by ourselves, and governments have had to step in with rules and standards. So, like there's examples of appliance safety and radio frequency spectrum and the environment. So do you think that your set of patterns will eventually become the basis for future government standards?
Thanks for your question. So this paper is just contains a very initial version of pattern. We're actually working on like more broader view of the patterns. We include governance patterns, which is for like AI industry, also for AI organizations, for the AI development team. So there are different governance patterns. For example, one pattern for industry level governance is independent oversight. and we can also consider ethical certification or maturity model. And we also have process-oriented pattern or product design pattern. So process pattern and the product design pattern are more for developers to use, but the governance pattern can be for different stakeholders in AI systems.
Thank you.
Thanks.
And we have a question for Suman. Using your mapping from APIs to phases, can we label phases of any Python data science / ML project that uses common ML libraries? Or are there any constraints to projects this tool can be applied?
Okay, yeah. So is like underlying assumption that the program or the software is using actually the common libraries. So we have looked at a few libraries like scikit-learn, Keras, PyTorch, TensorFlow, and so on. And many of those actually have very good documentation and categorization of the API. So if you go to the scikit-learn documentation, API documentation, you'll see that different classes have the APIs, like the class under the pre-processing class, there are different pre-processing APIs. Under the modeling class, there are different classifiers and other modeling related. So, and this is very common in other libraries too. So that helped us to very quickly do that. But in many cases, we had to do some extra work, like looked at the documentation and also the surrounding code of that API to make it valid. So oftentimes this was not automatically. So when we could not have a very good confidence, then we had to look at manually. So so yes, there is some constraints, but I think an automated tool could be built based on the existing documentation and the library's structure.
I have a question for Gaston. So all models are subject to interpretation. Do you think that your models could be misused as where someone superficially conforms to the model, but doesn't conform to the spirit or the intent?
Yes, I think that the model can use as a tool to support decisions. So every person who doesn't know how to apply security microservices, they can use the model to try to support decisions and take the best design decision in the microservice architecture, yes, perfectly.
But my point is, so for example, if I say I'm going to use a publish subscribe pattern because I want to keep the nice modifiability, extensibility characteristics that gives me, but then effectively I implement a call return style where every publisher is talking to a particular subscriber who then returns an acknowledgement back to that publisher. You've undermined the intent of the pattern, even though you're using the pattern. So that's what I'm getting at is do you have any thoughts about sort of model conformance that goes deeper than just saying, yes, we're using one of those?
Yes, we are exploring that options. We have a small experience using that model, but we can consider that path and try to figure out how to combine our model with other decisions that we have to take into the architecture. For example, the publish subscribe pattern. Yes, we can work in that field. Yeah.
Thank you. And we have time for maybe one more question.
Okay, so I can ask a question to Philippe. It's quite a specific question, but on an earlier slide, I think it might have been in your 20-minute talk, you had a diagram to the right of the Big Five diagram. And then in the latest slide, you had the diagram of the whole reference architecture. And I was unable to make any correlation between the two. Is there a relationship between those two diagrams?
Yeah, there should be. It's kind of difficult to explain. I know what you're talking about. We have this 5S framework, 4S framework, and the Big Five, and these are two conceptual frameworks that somehow frame how humans can interact, not necessarily with computer systems.